Wave theory, problems on uniform plane waves, series on electromagnetic field theory, lecture number 4.22. Uniform plane wave is an important class of electromagnetic waves. It is associated with certain properties like E, H, direction of propagation, forming a right-handed vector system, E to H ratio being equal to intrinsic impedance of the medium eta, E square by 2 eta being equal to overflow, and some more properties. It is also associated with surface impedance, depth of penetration, when incidence is on the surface of a conductor. In the present session, the focus is on problems and their solutions set around the features of uniform plane waves and its incidence on the surface of a good conductor. To begin with, we consider a problem example 1. Electric vector of a wave traveling in free space is given by E equal to 10y cap plus 5z cap cos omega t plus 2y minus 4z. Find angular frequency, that is omega, wavelength, that is lambda, magnetic field, that is h, and time average power in the wave. Solution process. From the expression, this is the expression from the expression, magnitude of phase shift constant is beta is square root of 2 square plus 4 square. It turns out to be root 20. Angular frequency omega is velocity multiplied by beta. Wave is in free space, so velocity is 3 into 10 power 8. Beta is already computed. Therefore, omega can be calculated easily. It turns out to be 13.42 into 10 power 8 radians per meter. Wavelength is 2 pi by beta. Beta is known, so lambda can be found without any difficulty. It turns out to be 1.40 meters. Direction of wave propagation can be found as 1 by square root of 2 square plus 4 square minus 2y cap plus 4z cap. It gives 1 by root 20 minus 2y cap plus 4z cap. Propagation direction cross electric field gives direction of magnetic field. Propagation direction we have just now calculated. Electric field is already available. So we can consider the cross, and also the ratio of electric to magnetic field is 125 because it is free space medium. E naught is 125 ohms. Hence amplitude of magnetic field is this. This pertains to direction, this pertains to ratio, E to H ratio. It turns out to be minus 0.03 x cap amperes per meter. Magnetic field then can be expressed as H equal to minus 0.03 x cap cos omega t plus 2y minus 4z amperes per meter. Time average power in the wave, it is Poynting vector of real part of E cross H conjugate complex Poynting vector. E is known, H, and hence H conjugate is known. So E cross H can be computed. P is half real part of E cross H conjugate. It turns out to be minus 0.075 y cap plus 0.15 z cap watts per meter square. Now we move to another problem, example 2. Magnetic field intensity associated with a plane wave in free spaces. Here there are two parts. H equal to H naught, X component, Z component. X component is cos 9 pi into 10 power 8 t plus 3 pi y. Z component is sin 9 pi into 10 power 8 t plus 3 pi y. Find frequency, wavelength, propagation direction, and associated electric field vector. Solution. We are required to find out frequency F. F is omega by 2 pi. Omega is, by just mere watching the expression, omega is this one, 9 pi into 10 power 8. By 2 pi gives F. It turns out to be 450 megahertz. B. B is wavelength. From the field expression, phase shift constant can be found as 3 pi. See, this is 3 pi. Thus, wavelength lambda becomes lambda equal to 2 pi by beta. It turns out to be 2 by 3 meters. Next, we have to find out the direction of propagation. By observing the expression, notice sign is plus and y, therefore it is minus y direction. Then at the end, we have to find out electric field. So see, from the field expression argument, plus is there, y is there, therefore direction of propagation is negative y direction. D. Magnetic field is given. This can be expressed as two components, two parts. H equal to H1, H2. H1 is in X direction, H2 is in Z direction. H1 gives one component electric field, H2 gives another component of electric field. These two components of electric fields together gives the total electric field. Then how to find out this electric field components? For the first term, direction of propagation is negative y, direction of magnetic field is positive x, and hence direction of electric field, it must be negative z. Amplitude of electric field must be 120 pi times that of magnetic field. Keeping these two aspects in mind, one can simply write down E1 as minus E naught H naught cos 9 pi into 10 power 8 t plus 3 pi y z cap. In the same manner, same way, E2 corresponding H2 can be written. It turns out to be eta naught H naught sine 9 pi into 10 power 8 t plus 3 pi y x cap volts per meter. Adding these two terms gives the complete expression for electric field in the wave. We consider another problem. Example 3. Electric field intensity in a plane wave traveling in a medium is given by Exzt is 10 cos 2 pi into 10 power 7t minus 0.1 pi z volts per meter. Calculate propagation velocity A and B dielectric constant of the medium and C associated magnetic field intensity. Solution. By observing the field expression, omega is 2 pi into 10 power 7 radians per second. Phase shift constant is 0.1 pi. From the values of these two parameters, velocity V can be found. V equal to omega by beta. Omega is known, beta is known. Ratio can be calculated. It turns out to be 2 into 10 power 8 meters per second. Note that it is less than 3 into 10 power 8 meters per second. So this is not a free space medium. Its dielectric constant B is required to be found in B. How? V velocity of the wave is C velocity of the wave in free space over square root of epsilon r. Solving this relation, one can find very easily epsilon r equal to 2.25. Now see, here wave is traveling in positive z direction and the electric field is in positive x direction. Magnetic field then must be in positive y direction. Ratio of the amplitudes is E naught by 1.5. What is 1.5? It is square root of 2.25. So, ratio of amplitudes is 120 pi divided by 1.5. Incorporating these two aspects, expression for magnetic field becomes HYZT equal to 15 by 120 pi cos 2 pi into 10 power 70 minus 0.1 pi z amperes per meter. Another problem, example 4. The electric vector in a uniform plane wave propagating in a perfect dielectric medium with a epsilon equal to 9 epsilon naught and mu equal to mu naught is given by this lengthy expression. We are asked to find A, the frequency, B, propagation direction, C, wavelength along propagation direction, D, wavelengths along x and y directions, E, apparent velocities along x, y, z directions. Solution. A, frequency of the wave. By observing the field expression, we can easily notice omega is 16 pi into 10 power 6 radians per second. Linear frequency is omega by 2 pi. Omega is known, 2 pi divided, we get 8 megahertz. B, propagation direction. Direction of propagation. From second part of argument, that is this part, it can be noticed the wave propagation has components in all the three directions. Unit vector along the direction is this. B cap is 1 by root 3 plus 4 plus 9 square root of 3 x cap minus 2y cap minus 3z cap. It turns out to be 1 by 4 root 3 x cap minus 2y cap minus 3 z cap. C, wavelength along direction of propagation. Medium here has epsilon r equal to 9 and hence velocity becomes V is C by root 9. Thus wavelength is lambda is B by F. V is known, F is already calculated, so lambda can be determined without much difficulty. It turns out to be 12.5 meters. D, wavelengths along x, y and z directions. Wavelength along x direction is lambda x is equal to lambda by cos theta. Here theta is angle between direction of propagation and x-axis, which can be found from cos theta is equal to beta cap dot x cap magnitude. It turns out to be root 3 by 4. Thus, lambda x is equal to 12.5 into 4 by root 3. It turns out to be 28.87 meters. Similarly, wavelength along y direction with theta between y-axis and wave propagation is lambda y equal to lambda by cos theta. It turns out to be 25 meters. Similarly, wavelength along z direction can be found. It turns out to be 16.67 meters. E. Apparent velocities along x, y, and z directions. Velocities in various directions are products of frequency with wavelength in those directions. We have wavelengths lambda x, lambda y, lambda z available, frequencies available. So simple multiplication leads Vx, Vy, Vz, resulting in velocities along those directions. Another problem, example 5. Determine amplitude h0, phase shift constant beta in a traveling wave with the field intensities E, H. They are given when medium is free space. A. B. Dielectric with epsilon r equal to 2.5. Also determine power density, electric, magnetic, and total stored energy densities in each case. From the expressions, we can notice if we consider plus sign in the field expressions, it gives a wave traveling in negative z direction. If we consider negative sign, bottom 1, then it gives wave propagation along positive z direction. With this understanding, let us move. From the given data, amplitude of electric field, angular frequency, phase shift constants are. This is amplitude of electric field. Here, pi is missing. Omega is 10 power 8. Here 10 power 8 is there. Here also 10 power 8 is there. A. And phase shift constant. Phase shift constant is simply beta. We have to find out its value. So, E naught is amplitude of electric field 30 pi. Omega is frequency. A. We consider first free space medium. Considering plus sign results in negative z direction traveling wave and negative sign implies plus z direction traveling wave. Let us consider first plus sign first. H naught is E naught by eta, 30 pi by 120 pi, because medium is free space. Therefore, eta is eta naught, it is equal to 120 pi. So, H naught is 0.25 amperes per meter. When we consider positive sign, wave is traveling in negative z direction, electric field is in plus x direction, and hence magnetic field must be in minus y direction, giving H naught equal to minus 0.25 amperes per meter. For negative sign, wave is traveling in plus z direction, electric field is in anyway plus x direction, and hence magnetic field must be in plus y direction, giving H naught equal to 0.25. Next, phase shift constant beta is to be evaluated. Beta is omega by V. Omega is available. V is as medium is free space. V is 3 into 10 power 8. So beta turns out to be 0.33 radians per meter. Amount of power flow or density is given by this formula. P is E square by 2 eta. E is 30 pi. Eta is 120 pi. Substitution results in 11.78 watts per meter square. Electric, magnetic, and total energy densities are. Electric energy is 1/4 epsilon E square. Epsilon is epsilon naught. E is known. Substitution results in 19.65 nanojoules per meter cube. WH is 1/4 mu H square. Here mu is mu naught. H is known to us. Substitution results in 19.65 nanojoules per meter cube. Notice electric energy density, magnetic energy density, they are equal. It is not accident. Half of the energy of the wave is in electrical form, half of the wave energy is in magnetic form. That's why here they turn out to be same. Average, total average is electric plus magnetic. It turns out to be 39.30 nanojoules per meter. B. Dielectric medium with epsilon r equal to 2.25. In this case, eta is 120 pi by square root of 2.25. It turns out to be 80 pi ohms. In the case of minus z direction traveling wave, amplitude of magnetic field becomes H naught equal to E naught by eta, 30 pi by 80 pi. It turns out to be 0.375 amperes per meter. For wave traveling in minus z direction, H naught is minus 0.375 amperes per meter. For wave traveling in plus z direction, H naught is 0.375 amperes per meter. Note here we are using the fact that electric field, magnetic field and the direction of propagation in a wave form right-handed vector system. Using this particular feature fact, direction of H is determined. Next, phase shift constant beta is evaluated. Beta is omega by V. Omega is known to us V. Here V is C by root epsilon r. Root epsilon r is 1.5. Therefore, beta is 0.50 radius per meter. The amount of power flow or density is P is E square by 2 eta. E is known, eta is known. Substitution results 17.67 watts per meter square. Electric, magnetic and total energy densities. Electric energy 1/4 epsilon E square. Here epsilon is 2.25 into epsilon naught. Substitution results in a WE being 44.20 nanojoules per meter cube. WH, of course, same amount results for WH also. Average is sum of these two. It turns out to be 88.40 nanojoules per meter cube. Another problem, example 6. For a non-magnetic soil with a dielectric constant 81, find propagation constant, skin depth, surface impedance, intrinsic impedance when its frequency and conductivity are given. A, in case of A, frequency is 60 Hz, conductivity is 10 power minus 2 moles per meter. B, frequency is 6 megahertz, conductivity is 10 power minus 3 moles per meter. Solution process. A, first we consider frequency 60 Hz and conductivity 10 power minus 2 moles per meter. In this case, sigma by omega epsilon turns out to be 3.70 into 10 power minus 4. Sigma by omega epsilon is loss tangent or dissipation factor. It is very, very large. In this case, 3.7 into 10 power 4, very, very large when compared to 1. Therefore, this is a good conductor. Medium is a good conductor. When medium is good conductor, values of attenuation and phase shift constants are same. Substituting the given values, one can find alpha equal to beta equal to square root of pi f mu sigma. All are given. It comes out to be 15.40 into 10 power minus 4. Once alpha and beta is available, gamma can be found within no time because gamma is alpha plus j beta. So gamma is available. Now depth of penetration for good conductor is 1 by alpha. Alpha is available. After substitution, it can be found equal to 650 meters. The surface impedance is square root of omega mu by sigma with an angle equal to 0.785 radians. Omega is known, mu is known, sigma is known. Substitution results surface impedance. The intrinsic impedance is same as surface impedance. You have to note down this point. Now we come to B. Frequency is 6 megahertz, so the dissipation factor or loss tangent is 3.72 into 10 power minus 2. It is very, very less when compared to 1. Hence, the medium can be considered as a dielectric. Using the given values, the propagation constant can be obtained as first calculate omega mu, then omega epsilon. Gamma square is j omega mu into sigma plus j omega epsilon. Sigma is available. Substitution and a little bit of manipulation results. Gamma square as 0.0499 at an angle of 1.89. But we want propagation constant gamma. So we have to apply square root. It results in gamma equal to 0.13 plus j 0.18 per meter. Real part is attenuation constant, imaginary part is phase shift constant. Skin depth and surface impedances. Skin depth is 1 by alpha. It turns out to be 7.69 meters. And the surface impedance is gamma by sigma. Gamma is known, sigma is given. Substitution results in 0.13 plus j 0.18 kilo ohms. These are some of the problems which I want to discuss with you. These are the problems, as already mentioned, set around uniform plane wave propagation and uniform plane wave incidence over a conductor surface.